Welcome to Part 3 in the module on patterns and frameworks for asynchronous event handling. In previous parts of this module, we first discussed the Proactor pattern and then described how ACE provides a framework called the Proactor framework in order to implement this pattern in a portable and efficient way on multiple operating systems that support asynchronous I/O. Now we're going to apply the ACE Proactor framework to JAWS to indicate yet another path through our pattern language for high-performance web servers. This particular path is going to demonstrate the use of asynchronous I/O as a way to be able to initiate connections, handling of connections, and be able to handle asynchronous read and write operations that take place after asynchronous connections are completed and established. Let's first take a look at the architecture of our overall solution. We'll be focusing primarily here on the use of the ACE service handler and ACE Async Acceptor, as well as the ACE Proactor framework, of course, in order to be able to carry out this asynchronous processing. If you take a look at the structure of the solution, it looks quite a bit like the reactor pattern solution, except unlike the reactor pattern, we're driving everything by asynchronous operations using completion events as opposed to synchronous operations using initiation events. Notice also that even though we only have one thread of control in our solution, it can still scale up quite nicely on operating systems that support asynchronous I/O, such as Windows. So let's first start talking about the classes involved here. We're going to implement a class called the HTTP Async Handler, which inherits from ACE Service Handler. And what this allows it to do is it allows it to be able to implement various asynchronous operations to implement the HTTP protocol processing. We define a number of data members. We define a pointer to the ACE Proactor. We cache away to keep track of that relationship. We define a memory mapped file abstraction we can use to efficiently keep track of files that we map into memory. We keep track of the handle, that's the socket endpoint that we're going to be connected to, and so on. And we also define something called HTTP request, which is simply a little wrapper around the ACE message block abstraction that's used by the ACE Proactor framework to be able to send and receive data very efficiently without having to copy large chunks of data and be able to deal with things very fast with respect to chaining messages together. We also have a pair of data members here that are an ACE async read stream and ACE async write stream. And we will use these to invoke asynchronous read and write operations respectively in order to carry out the processing without blocking the server thread for the duration of the call. Let's now take a look at the OpenHook. This is the hook method called back by the HTTP Async Acceptor in order to be able to activate our HTTP Async handler once a connection has been established passively. What this particular approach does is it first opens the read stream and it associates with the read stream the handle that we're reading on as well as a reference to this object, which will be used to indicate where the completion events need to be sent to when the asynchronous read operation is done. We then turn around and kick off the asynchronous read operation, passing in the message buffer that we've allocated to store the results that come back from the client application. Here then is the handle read stream hook method, which is dispatched by the Proactor framework when that asynchronous read operation that we initiated completes. We'll talk shortly about how the connection is made between the initiation of the asynchronous read operation and this completion event hook method that gets dispatched by the Proactor framework. But be that as it may, assume it gets called back. And what we do now is we go ahead and we check to see whether or not we've gotten a complete request from the client. And if we have got the complete request, we're going to go ahead and handle that complete request. If we have not got a complete request, if we've only got part of a request, then we go ahead and reinitiate another asynchronous read operation in order to be able to get the complete request. And this may take place actually for a number of cycles until we're able to read the entire request from the client. Assuming we've got the complete request, then the handle request method is called, and this is going to do a couple things. The first thing it does is it checks to see what kind of request we've received. So keep in mind these things are initiated asynchronously, and we could have asynchronous receives for GET requests, POST requests, PUT requests, and so on. Let's assume for sake of argument that we've got a GET request. So if we have a GET request, what we do in that case is going to be very familiar. We take the file name that we got that came in the request from the client that we extracted out of the stream once it was read asynchronously. We memory map that file, and then we turn around and we initiate an asynchronous write operation. This asynchronous write operation, of course, will attempt to send the entire file back to the client asynchronously. Notice that we've used a write operation here. We could also have used the transmit file mechanism. Transmit file is a very interesting mechanism available with Windows and also available on a number of POSIX machines and Unix machines now via the send file system call. And what it does is it takes open file handles, an open file handle to an open file handle to an open socket, and it does an asynchronous operation to transmit the entire content of the file to the socket in one fell swoop. So that's a nice way of being able to use and leverage the underlying hardware and device driver mechanisms for efficient data transfer, things like device memory mapped I/O and various kinds of other ways of transmitting data without incurring context switches, copies, and other kinds of overhead that you typically incur if you did this one buffer or one chunk at a time. Here is the HTTP async acceptor. It inherits from ACE Acceptor, Async Acceptor, and the ACE Async Acceptor works very much like the way that the Acceptor connector framework did earlier when we talked about the ACE Acceptor and ACE connector. You can basically parameterize it with the kind of service handler that you want to have it create. In this case, it's an HTTP async handler. And this then serves as a factory for passively accepting connections, initializing the handlers, and then being able to have those handlers activated to do their thing. In this particular case, the constructor for the HTTP async acceptor will simply delegate up to the underlying ACE async acceptor and call its open method. And this open method takes a number of parameters. The key parameters it takes are the address it wants to listen on for incoming connections, typically port 80 in our case. And it also indicates some other things. It indicates whether or not it should go ahead and invoke certain operations, such as asynchronous accept calls. And it says how many of these calls should be invoked. For example, in this case, we're going to have some kind of backlog number of them, perhaps 5, that will kick off simultaneously. And it'll also indicate that we're going to keep reinitiating these calls automatically as they're being connected with clients. So we'll always have a number of asynchronous accept calls that are ready to go in case a client connects to our server. We also pass in the Proactor, and that's in order to get access to the I/O completion port that it holds internally, that it uses in order to match up the completion events with the original requests that were invoked asynchronously. So a lot of things going on in this simple constructor, but you don't have to really worry about the details. That's all handled for you internally by the ACE Proactor framework. Finally, we have our main program. As you can see, it's very simple, not unlike the reactor examples we've looked at before. What we do is we go ahead and set up the addressing to listen on port that's important for the web server, like port 80. Then we create ourselves an instance of the HTTP async acceptor, passing in that internet address, passing in the Proactor. As you just saw, that will kick off the asynchronous accept operations, however that is done on a particular platform. And after those asynchronous accept operations are kicked off, then we go and run the main Proactor event loop. And all that does is it just sits there waiting for completion events to occur as clients connect and as read operations, write operations that were invoked asynchronously complete, as well as, of course, other accept operations that may complete likewise. So that's really all there is to it. Very simple, very streamlined way of writing the server program. As I've often said, it's sometimes a little bit hard to understand the interactions between various pieces by looking purely at source code. So here's a sequence diagram that illustrates the various interactions between the components that I've demonstrated and illustrated in the previous code. So as we see here, the web server starts out by creating an HTTP async acceptor, and that will go ahead and initiate the async accept operation on the underlying asynchronous operation processor, such as the operating system like Windows or POSIX that supports asynchronous I/O. It then turns over control to the Proactor, and when a connection shows up, callbacks are driven to the HTTP async acceptor in order to create an appropriate HTTP async handler. So that's all part of the service initialization and connection establishment phase. Once that connection's been established and the handler's been created, from that point onwards, for the duration of that particular conversation with the client, we will then drive the communication by asynchronous read and asynchronous write operation calls. So we'll do an asynchronous read call to get the data from the client, and we'll do asynchronous write calls once we've received the URI in order to be able to transmit that back. And you can see, if you look carefully at this sequence diagram, the various ways in which the pieces talk back and forth to each other to carry out the processing in a solely asynchronous manner. So to summarize this part of the module, the ACE Proactor framework alleviates some of the bottlenecks with reactive I/O because things can run asynchronously. We can also have some threads in a pool to kick off new asynchronous operations in a concurrent way. This also can alleviate some of the complexities of synchronous multi-threading because we can write our programs often to have few or no locks required because everything's driven asynchronously and all the concurrency is handled largely inside the operating system kernel. The framework allows applications to invoke I/O operations asynchronously in two canonical phases. The first phase is the initiation phase, where they kick off the operations on the asynchronous operation processor, such as Windows, doing things like accept EX or read file, write file EX, and so on. These are all operations that are part of Windows. We can abstract away, of course, using the ACE Proactor framework to hide those details, but under the hood, that's what's being used. So that's how we kick the operations off asynchronously. And then the second phase is when those operations complete, we can go ahead and handle the demultiplexing and dispatching of those completion events back to the appropriate completion event handlers, which in our case would be the acceptor for accept events and the various async handlers to do reading and writing of the actual data from the clients. So that illustrates how we can apply this particular pattern in the context of JAWS using the ACE Proactor framework. And next we'll talk about yet another pattern that's often combined with Proactor in order to handle the multiplexing of responses for completion event handlers very efficiently.